One second. All right, here we go. Got it, found it. So this is a perspective grid. This is how we see the top ramps down, sides ramp in, bottom ramps up. And so here we are. So I'll put my guy here. This is his eye line here. And I'll throw this mountain in here. Let's just say it's 3,000 feet above him. Okay?
Sure.
So the mountain's 3,000 feet above him. He's standing right next to it. The sun is above the mountain. And the sun is just going to move away. Now, is the sun below the horizon or just beyond the mountain?
Just beyond the mountain.
Of course. So if he went up in the air, he could see over the mountain and see the sun again.
Yeah.
Or if he went backwards, he'll change his angle to the sun and he'll be able to see it. So we move him 25 miles away, and now that's what he sees. So his twin is 25 miles behind him, and he sees the mountain here and the sun up there because he has a better view. This guy, the other guy, is standing at the base of this mountain and he can't see the sun because it's beyond the mountain. Right?
Again, probably not to scale, but yeah.
Not to scale, but this is absolutely super easy. So the top of this mountain is 3,000 feet over his head. Even if the Earth was a globe at 20 miles, you can take, 3,000 feet above his head. You can take, 50 feet off, whatever. But the mountain is still well above his eye line, but he sees it and perceives it as the horizon of the Earth.
Sure. Yeah, okay. Because at that distance, you wouldn't be able to tell the difference between
right. The height and everything compresses into the horizontal eye zone or horizon, right? The horizontal eye zone. So if the sun goes farther away, is it below the Earth curve or is it beyond the mountain?
I mean, at that point, I would say, if you want me to be honest, I would say probably behind the curve at that point.
Well,
based on that image, looking at the compression of that image.
He's looking up at the mountain. So that line of view is really going up, but he perceives it as level. So if he went up in the air, he would see it again. I actually have footage. Hopefully I can find it, where it sets, just like you say. And I set my drone up and there was the sun again. I'm going to show it to you in a minute. so hold on.
Let me just get that concept right. So you saw the sun from your eye level?
Yep.
Lower over the curve, and then you put your drone up how high?
Not very high at all.
Roughly, just not very high, but high enough. And
up 100 feet. I'm not seeing over the ball. I'm seeing the sun, and the sun will set above the horizon at that point because it's going into the atmos. So we got the mountain 3,000 feet above his eye line. Looks like it's at his eye line, and we have the clouds. Now the clouds are, 5,000 feet over the mountain. The sun is higher than the clouds. So all the clouds merge into this horizontal eye zone, and the sun goes away. Did it go below the Earth curve or beyond this line? It's beyond the line. Again, you think it's the Earth curve, but
practically, yeah, it's beyond the line. It's beyond the line. Yeah.
So this line now is not only 3,000 feet high; it's 5,000 feet above that. So there's 8,000 feet. A minimum of 8,000 feet above his eyes, and the sun just went beyond it. It just went beyond it. If we went up,
run those numbers by me again.
So the mountain is 3,000 feet high. These clouds, let's say they're 8,000 feet up, whatever. Okay, 5,000 feet over the mountain.
Yeah.
So these clouds are also merging into this line. So this line now is made of opaque atmosphere that looks like it's at his eye level. But it's really
it comprises 8,000 feet.
It's 8,000 feet. And now when something goes beyond 8,000 feet, it's going to just go away. It's going to be beyond it. So let me get my so here's an example. We got a camera on a table. Rid of that. And it's just taking this coin away. Now we're slightly below the table. Makes sense why it's disappearing from the bottom up, right? Well, I just proved that this line is not at your eye level. It's thousands of feet above your eye level. And this is what you're seeing. The half sun just disappearing beyond something that's above your viewing level. But it appears, due to perspective, to be at your viewing level, right?
So how would that compute to sunsets over the ocean horizon, which is flat? Yeah.
Well, that's
to our eye level.
Think. All right. So, oops. All right. So
Because again, if I could just kind of briefly expand on my thoughts in that regard, because I'm thinking if it's a flat plane kind of that stretches out as far as our vision can see, it would get smaller and smaller and smaller and smaller and smaller until it just disappears into obscurity.
I can show you. After I show you this, I'll show you a dozen videos of the sun getting smaller and smaller and smaller and disappearing into obscurity of the horizon.
But that's difficult for me because I've seen it where it doesn't do that.
And as we explained before, sometimes it does, sometimes it doesn't, depending on the atmosphere and how far you're actually seeing. That horizon could be 10 miles away, it could be 50 miles away, it could be 150 miles away, right? Depending on what's going on. Are there mountains in the distance that you can't see because the light bouncing off the mountain isn't making it to you? I'll show you that also, right? So again, it's easier to believe that the sun's going behind Earth curve because you don't have to think anything beyond that. But I'm teaching you that there are better and clearer explanations that don't defy the physics of a ball 24,901 miles around. How high is this cloud? Can we say 8,000 feet?
About that, cumulus clouds, yeah.
Yeah, okay.
Yeah.
How high is this cloud?
Probably about the same.
Yeah, and the ones in the distance here? Same.
Yeah, probably about the same.
But eventually, if we doubled this distance to this cloud, it's going to be it's merged into this black line, right?
Yeah.
Okay. So when I look up, I see blue sky because I'm not looking through, I'm just having a clear view. As the light attenuates, as I look down lower and lower, I'm looking through more and more and more atmosphere. And the color, I see the red sky because the light is being absorbed by the atmosphere. Blue sky here, but somebody over here on this, where this horizon, apparent horizon is, they look up, see blue sky. They don't see red sky, right? They see blue sky. Right, so this is the light attenuation. So you got a cloud here, got a cloud above me, and this cloud goes into the distance. I'm losing the angular resolution. This cloud is probably just as wide as this cloud, but because of my angle view, it gets tighter. And if I add another cloud here, right, it's getting harder and harder to see the bottom of that cloud. And I add one more, I just added one on the horizon. You can't even see it. It's literally become horizon and it's black. It just becomes the horizon, right? So, and even without clouds, the atmosphere is doing that. I'm just using clouds to show you, but the atmosphere literally will compress into an opaque line that we call the horizon or the horizontal eye zone, not the curve eye zone, the horizon. So the sun's above the clouds. And as the sun moves away, it's going to set from the bottom up beyond this cloud. Look, it's disappearing from the bottom up. Now, is there any difference between that cloud and this cloud? No, it's going to disappear from the bottom up. But I'm going to be able to see it again because this cloud's giving me some blue sky space. But then this one is going to disappear from the bottom up. But this one, I can't see anymore because it's merged into the horizon and it's just going to go beyond the horizon, right? So here is, again, I'm just showing you more clouds merging into this horizontal eye zone, right? They're just getting merged. Now, this is a tree line. I'm on the water, so these trees are higher than the water. But if I double the distance of those trees, I won't see the trees. They're still above the water, and they just merge into a horizon, right? These clouds are going to merge into the horizon and the sun will just go beyond them, right? See these clouds here? They're merging in these real life photos. And as the sun goes away, it's just going to go beyond these trees, beyond those clouds, and it's going to disappear from the bottom up. Just like you showed me that, this thing, the sun going down, right? That's what's going on. Look, the sun disappeared from the bottom up here, and it'll pop out here, and then it'll disappear beyond these trees. Beyond those trees. So here's the one I wanted to show you. So here I am. Now, these trees are obviously higher than the water, right? But this is just like 5 miles away. But to the left, I can see 20 miles away, the shoreline, and I can't even see the trees. They literally become the horizon, but they're still above the water, right? So now I send my drone up. This is 10 minutes after the sunset, and there's the sun again. And it's just sitting there. Now, I saw it go down at a good clip, and then it just stopped, and it's not going any lower. I'm going to zoom in, and look, what is this? It's just literally disappearing now. Everyone on the water saw the sunset from the bottom up 10 minutes ago. I'm still looking at it, just a couple 100 feet in the air, so I can see over. It's a super clear day, and it's just disappearing. These are mountains in Pennsylvania, hundreds of miles from me, and the sun is just going beyond the Atmos. That's all it is.
So, okay. Yeah, I mean, it's certainly interesting. I can't really give an opinion because I'm not a meteorologist. I don't know this stuff.
Well, here's the thing. A meteorologist is indoctrinated into believing what he believes. You're a man with God-given common sense, right? God-given common sense. You're told that this is the horizon of the earth and the sun wait a minute, the sun's coming from above it. How come it didn't come from below it? And by the way, the sun is mirrored. The horizon's really here. Okay, Atmos horizon's really here, and the sun is just literally coming from beyond this atmospheric deck, which is thousands and thousands of feet above your head. You're sitting in your yard, and there's a fence on the other side of your yard, 5 feet tall, and your neighbor comes, he's talking to you. When he walks away, he's going to disappear from the bottom up. The fence is going to look like it's at your eye level, but he's going to disappear from the bottom up. Does that mean his yard is curved, or is he just walking away from the fence? It just appears above the horizon. Right? Now, let me show you why.
I don't know.
Why? Well, I don't know is okay, but you have the ability to learn. Now, why is this train getting smaller?
Because it's getting further away, so it appears to be getting smaller.
But you expect the sun to do that, right? You can say yes.
Yeah, well, you would do, yeah.
Yeah, well, no, you expect it. Don't say it. I'm going to teach you something. So the train gets smaller because we are at the same level of the train. I forget the principle. I think is it the Bernoulli's principle. So this is a wall. All these lines are parallel. These lines here, these lines are parallel with this line. But this is how we see. So perspective makes things appear to go down. So here's a side view of this guy, right? No one ever sees an orthographic side view in reality. So when the sun goes away, you'll see the sun will appear to go down from this guy's point of view. But this is a side view of what's actually going on. And then the sun will just disappear, as I showed you, beyond the horizon. Now, here's the train car, and the train car gets smaller because it's getting higher and farther away. When something's already farther away, it's already smaller. And as it goes away, it doesn't get much smaller. And as it goes down, it's getting into thicker and thicker and thicker atmosphere. It might start expanding just due to magnification. So here I have two wiffle balls, one right here, one 6 feet away. This one is smaller than this one. So this was the sun and it's going away. It should get smaller, right? Makes sense. But
in theory, yeah.
In theory, well, in what you were saying, making you believe we live on a globe. So when I lift up the camera here, I'm not going to get any closer to that ball. I'm just going to go up. So this ball has some distance. And as I go up, come on. So when I go up, this ball is going to get smaller. I'm not getting any closer to this ball. And when I get up, they both appear about the same size. A little different. And sometimes we see the sun different. Sometimes we don't. But here they are. They're about the same size. And if we're down here looking at the farther sun, all that Atmos, all the water in the Atmos will appear to magnify the sun. Maybe it magnifies it in a perfect yin-yang, like, hey, it didn't change size. But in reality, in your globe model, when the sun is going around, we're spinning, but I'm just going to go, the sun's coming around and it's just going around the earth like this, right? It's going around the earth like that. From noon to sunset, how much farther from you is the sun in percentage? 93 million miles away. It's just maybe 2 or 3 or 4,000 miles farther away. So the 0.0001% smaller, whatever it is, it's something stupid, right? So in the heliocentric model, it should not shrink. So we use a solar filter, 1 million solar filter,
right?
And we film the sun going away. The problem is the real part that you want to see the solar filter when the sun is really near the horizon, that's when you get the most information. The solar filter makes it so you can't even see the sun, right? But this got 23% smaller. There's no point in the heliocentric model that the sun should get 23% smaller, right? This is another one. We filmed it, and it, as it's going away, its light is attenuating, and it's getting smaller. And when
this is as it's setting.
Yeah, as it's setting, I think someone got it. It might have been more than 23. I'll just go with the 23. It's smaller. And in the globe model, there's no explanation for that whatsoever. There's no explanation for that at all.
I would, if I was to guess, and as I say, I'm not an expert in any of this sort of stuff, but if I was to guess, I would say on a globe model, as the Earth is set, as the sun's setting over the curve, assuming there is a curve on a globe model, otherwise it wouldn't be a globe model, it's the angle of the light is having to come through a lot more atmosphere rather than kind of more direct down. So I would probably guess definitely that there's some kind of optic light tricks going on, but I can't say
the globe model requires optic light tricks. Okay, so here's a mountain. Here's the globe, right? I bring this over the mountain. The mountain's behind the curve, right? So you don't have to believe anything. You can go verify this, but this is a spot in Aluja, France, and we're looking out over the ocean. From this spot, Mount Canigou is 175 miles away. And using the Globe Earth calculator, the top of the tallest part of Mount Canigou should be over a half a mile below the curve, just like I brought that bottle below the curve, right? So the sun migrates between the Tropic of Cancer to the Tropic of Capricorn every 6 months, 6 months in, 6 months out, and twice a year, the sun will line up with this viewing spot in Mount Canigou. Now, do you see me right now?
Yes.
If I turned off every light in this room, could you see me?
Probably not.
So you're seeing the light that's bouncing off of me.
Yeah.
Okay. The light that is hitting me, the source of that light is brighter than the light that's bouncing off of me.
Sure.
A brighter light can push farther through the atmosphere. Okay, easy. That's true on flat or globe. So Mount Canigou is 175 miles out here. It's in the light, but the light that's bouncing off of Mount Canigou either can't push through the atmosphere or it's behind the physical curve.
Say that again, sorry?
The light that's bouncing off of Mount Canigou, either the Earth is flat and the sun and the light can't push through 175 miles of soupy atmosphere, or it's blocked by the curve.
Sure.
Okay, so on your...
Or a mixture of both, perhaps.
Well, if it's blocked by the curve, doesn't matter how bright it is or not.
Well, when you start to invoke refraction and things like that, but yeah.
So refraction. So refraction compresses things, warps things, mirages things. It does all sorts of things, but one thing refraction doesn't do is make things that are physically blocked appear above that physical blocking. If we're on a big field and we're 10 feet apart and we're looking at each other, no problem. If I put a 10-foot brick wall in between us, you can't see me. So we both started walking backwards. How far would we have to go? And what type of weather front would need to come in before I can see you above that wall?
I have no idea.
Well, you have no idea. It's not because you're stupid. It's because it's stupid, right? You would never see me again.
Well, but true, but I couldn't infer that because I don't understand it, that it can't be true. I might just not understand it.
I understand. Nobody has ever been able to show significantly a clear object behind a physical obstruction refract up. Yes, things can get compressed. I was looking at my wife and daughter down the beach about a mile